circumbinary disk, and that in itself is very interesting. Yes, right. Well, you know, there's something else that we should mention. A small fraction of stars, when you have quadruples, they're mostly double-double, right? A small fraction of quadruples are 1, 2, double, and then 3, 4. So you can actually have a sequence of this stuff happening, right? Okay, now I want to move on to the very last thing, which I'll only spend a few minutes on. And that is models for type 1a progenitors, which I think you've probably already gotten from the earlier part of the talk. So I just want to mention that the two models that we typically look at are single degenerate models in which a star donates mass to a white dwarf, and double degenerate models in which two white dwarfs merge. Once we introduce a third star that can give mass to these close binaries, we have, I would call it, a new model. Well, it is a new model, but I would call it a new model of second chances, right? Because just think about it. Suppose you have a binary, a compact object binary, two white dwarfs, but they're not close enough to merge in a Hubble time. Or they're not massive enough to produce a type 1a supernova when they do merge. Give them a third star, and a certain fraction of the time, as we have shown, they will develop the correct masses and separations that could lead to a double degenerate type 1a supernova explosion. On the other hand, start with such a system, and if one of the stars, one of the white dwarfs, gains enough mass during an episode of accretion from the third star, it may explode through what we normally think of as the single degenerate mechanism and become a type 1a supernova that way. And if you want to hear a really crazy possibility, okay, when the first white dwarf gains enough mass, it may not explode right away. The reason is that in addition to gaining mass, compact objects gain angular momentum. And so if the white dwarf has spun up so that its critical mass is higher than the mass it actually has, it may have to spin down so that its critical mass becomes equal to, let's say, the Chandrasekhar mass. So there could be a wait time. During that wait time, the companion continues to gain mass. So you could have a delay time to the supernova before the supernova occurs, and there could be a significant change to the other star. Maybe even it could gain enough mass to become a supernova. So this is kind of a crazy possibility, but there's nothing that says it can't happen. And we know in nature if it's possible, we should consider that it may happen. But I would put this sort of on the outer edge. Now, I've already gone through some evolutions with you, so I won't take the time to go through these, but I will show you this graph that I made, which shows you all of the possibilities, okay? You could start any place on this graph. For example, you could start with a black hole neutron star binary. Blue means that a blue line connecting two boxes means that a neutron star has undergone accretion-induced collapse and become a black hole. So we talked about that earlier. Or you could start with two white dwarfs. A red solid line means that a white dwarf undergoes an accretion-induced collapse to a neutron star. Both of these could undergo accretion-induced collapse, and if the accretion doesn't stop, they could both become black holes, right? Or a white dwarf that is a carbon-oxygen white dwarf might explode and become, let's go this way, a type 1a supernova in a binary that contains another white dwarf and potentially a donor star. Or, as I just said a few moments ago, they could both gain enough matter to become type 1a supernovae in a very unusual kind of situation. So what are the numbers? Well, this simulation includes, of course, neutron stars and black holes, but we can see that if you take a look at the number of systems where their merger time changed by at least a factor of 10, that white dwarfs become type 1a supernovae roughly a quarter of the time, 20% or 25% of the time. And only a much smaller number of systems in this simulation became black holes. You should not take this to be a prediction of anything at all, because this was an artificial simulation simply meant to explore the whole parameter space. To make these predictive, we now have to start with distributions that reflect nature, with distributions of initial conditions that reflect nature. But the possibilities are very rich. And so the take home from this part of the talk is that mass transfer from a third star provides two types of second chances for double degenerates to produce type 1a supernovae. And that's not even the end of the story, but I think it's really just about the end of the talk, so I'm going to give you the final take homes. So I think triples and higher order multiples are important parts of stellar populations. They're there, so we have to take them into account. Mass transfer from a third star can effect important changes in compact object binaries without fine-tuning. That's the key thing. That this may affect the rates and the characteristics of gravitational mergers. That needs to be explored. We are doing the exploration now for chemically homogeneous systems. Mass transfer from a third star can produce detectable and unique signatures. For the unique signatures, I think both Lynx and Lisa will play important roles. That motion of the inner binary influences mass leaving the donor, so that the pulsations of the Roche lobe exist and have important consequences for mass transfer. And that mass transfer from a third star produces a model of second chances for progenitors of type 1a supernovae. So I know I've said a lot here about a lot of different things, but there is a unifying theme, which is a process that has not really been well considered in the literature to date. And I think that puts us in the very fortunate situation of having a great deal to explore. So I'd love to chat with you if you have ideas about following this up or would like to hear more about what we're doing. Thank you.
Curious. Chuck Steidel said 80% of all relevant phenomena involve binaries.
That may not be an exact, it's a quote, but it may not be his exact estimation if he computed it.
What number would you put there for triples?
That's a very interesting question, because if you ask yourself for binaries, what fraction of binaries do these interesting things? Anybody who's worked with them and with binary processes knows that it's only a very small subset that get to do, become the type 1a supernovae, for example. It's something like maybe 1 in 100 or 1 in 50 white dwarfs that could become type 1a supernovae. And if you ask yourself the number of systems that are going to become close merging black holes, that's smaller. So triples have a chance to be important because they may play a role in helping binaries to get to these special end states. If you just go by the statistics of the population, you might say, okay, it's a 10 or 15% effect. But when you actually put in all the physics, which we're just beginning to do, it could be that they play a more important role.
Yeah, about the type 1a supernova stuff. And so the main reason the single degenerate model got into trouble was because people just haven't seen the donor stars.
Yes, yes.
And fewer, second chances sort of would increase the rate maybe overall, but it wouldn't solve that problem, right? Unless your donor stars are significantly smaller so that you can escape this bound.
Right, well, that's an interesting question. So let me just make a couple of comments about type 1a supernova signatures. So first, I think there are, at least in one case, there's pretty credible evidence that there was probably a symbiotic prior to explosion. I'm not quite sure where that evidence stands today. But if you'll notice, I spent some time talking about the spin up and spin down of the neutron star, of the white dwarf rather. If you have spin up, then the time to spin down means that the explosion takes place in a somewhat different environment. In particular, spin down can't begin if you have a giant donor until after the giant has given up its envelope and just become a core. It can happen in CV-like binaries, but by then the donor star is likely to be a very low mass star. So the signatures post-explosion that people have normally predicted for type 1a supernovae have not typically taken spin down into account. So I think it's a complex issue, and that evidence, so far we were in a situation where lack of evidence was taken as evidence of lack. That's not always correct. Yeah, Josh, I know you wanted to ask something.
So in these lovely simulations you were showing us, did you compute or extract the actual accretion rate onto either of the?
That's